Ogenerume Okolo. I'm going to be the moderator for this event. And, I welcome each and every one of us to this inaugural event today, being organized by the Society of Petroleum Engineers Abuja section. So it's actually a collaborative work being done by the young professionals of SP Abuja section and the Student Affairs Division of SP Abuja sections in order to be able to develop the skills of both the young professionals and students in SP Abuja section. And the event was also open to the globe, so the other students and professional members will be able to benefit from these 2 days training event. So before I commence the major formalities of the program, I would love to recognize the presence of some dignitaries in our midst today. I think the section chair is with us today. Ma, thank you for joining us. Good evening from Abuja.
Good evening, YP Chair. I'm glad to be here.
You're welcome. I think I'm also having Professor Deshin Fadero with us today. Prof, you're welcome, sir. And I also have other special guests that are present today. So as it has been displayed for us, you can see that the training that will be organized today is Subsurface Data Analytics. And we have very distinguished speakers who will do justice to this this evening and also tomorrow morning. As you can see the schedule. So we have one today, one within 1 hour to 2 hours. And also we also have another section that will take place at 11 a.m. tomorrow. So we have 2 eminent speakers for this event today. The first is Destiny Otto, who is a technical lead for TechBet Global Limited. And we also have in our house today, Praise Eke Power, who is a machine learning engineer for TechBet Global. So before we commence with the introduction of the speakers, I want to hear 1 or 2 words from our section chair. She has been very, very supportive towards the young professionals and the students in the section. So, Ma, do you have any word for us before we proceed with the program?
Yeah, just a few words. Good evening, everyone. Thank you for joining this program. And congratulations to the YP team for putting this together. It is indeed timely and very relevant. Well, all companies actually want to make profit. Because they are not charity organizations, especially in industries like ours, where the risks are very high, and of course the rewards too are very good. So, but particularly in our industry, data analytics is very important, because for us to get the best out of our reservoir, make maximum recovery, we need to really have a very good understanding of what the reservoir is. And studies have shown that data analytics and digital technology and all that have algorithms and all those. I'm not a very tech person, but studies have shown that the results you get from digital is the percentage is higher than when you use the empirical formulas that we've always used in the past. So I believe that this is a very timely thing that you people have brought together, and I urge all of us, and I'm also going to participate because I want to learn and I want to also get the certificate, because it's never too old to learn something new. So please, I urge you to make the most of this opportunity, because we're bringing all of these things in line with SPE's vision to empower its members, let the members get the best out of their membership and be more productive so that we can improve the industry and our nations at large. So I urge us to pay attention, get the most out of it so that we can be good ambassadors for the industry. Thank you very much.
Okay, thank you, Ma, for your brief remark. And Ma, you're always inspiring me to still keep on pursuing knowledge. But despite the schedule, you still want to learn and learn and learn. So if you can do it, I believe I can do it. And this also goes to everyone that we can do it. So that's why we have our speakers on board today who will do justice to subsurface data analytics. So I want to introduce the speakers today. So we have Destiny Oto, who is here with us today, and we also have Praise Ekeopara, who has joined us today. So for the profile of Destiny Oto is a vibrant and multi-talented young engineer. He's passionate about providing innovative solutions with cutting-edge technologies like artificial intelligence, machine learning in the oil and gas industry. He's also an expert in data analyst. He's an expert data analyst. He's a machine learning engineer. He works with Heritage Energy as a petroleum engineering data analyst. He previously worked with ExxonMobil Nigeria and South Crescent, which is a reputable oil and gas software development company here in Nigeria. He's the founder and technical lead of TechPet Engineering Global, a digital skills company based in Port Harcourt with 30 staffs. TechPet Engineering Global is committed to providing cutting-edge digital technology solutions and services, both to Nigeria and the globe. So he's a certified instructor and a software developer. Destiny is also a renowned conference speaker. He has spoken in many student and professional conferences, and he has delivered lots and lots of programs. He's currently the Young Professionals Technical Chairman of SPE Port Harcourt section. So a very warm welcome to Mr. Destiny Oto. I guess you have joined us. Mr. Destiny. Hello, are you with us?
Hello.
Yeah. So a very warm welcome. Yeah, I can hear you. I can hear you. A very warm welcome to you. So would invite you to take the floor at the moment. So you could tell us more about subsurface data analytics. Then when you are done, I will invite Praise Ekeopara, who would also wrap up the session today, along with the agenda that we have. So thank you.
Sorry, Mr. Rume, Mr. Ogolo, I cannot unmute. Can you, if you check, I think can you make me a host or give me that permission to unmute? Because I'm using my other device here. That's my system.
What's the name of the device? So we can make a co-host.
Okay. I think it's done now. I think it's done. Can you hear me?
Yes, we can hear you. We can hear you. You can proceed.
All right. Thank you very much. All right. Thank you very much. So I'm happy to be in your midst. I'm Destiny Oto, as he has already introduced me. So today we have something very, very amazing, and I just hope I'll be able to deliver as much as I really want us to get. Yeah. So I'm going to ask. I'm going to share my screen right now. Can you please let me know when you have started seeing my screen?
We see your screen, but please kindly put it on slideshow mode so that it could be enlarged.
Hello? Yeah, pardon, I think that's because of networking. Yeah, so while to this time, while I was testing it, I discovered that the network was terrible all of a sudden at this point. Yeah. So I will just introduce very briefly about, I'll just talk in less than 5 minutes about data analytics. Actually, the person to handle today is Praise Kopara, who will handle us on the session. But I just want to just give an intro, which I would actually continue tomorrow. Yes, a very basic intro on what we are going to be doing, after which Praise will take over from there. Yeah, by tomorrow I'll continue the session. So for data analytics, when we say subsurface data analytics, we are just referring to subsurface data, data not at the surface at this time. So that means all the subsurface disciplines included, right? So geology, geophysics, seismic and all that, and well logs and all that field that has to do with the subsurface. Yeah, conventional workflows. We use data-driven methods or techniques to solve the same problem. And just like the section, data-driven methods have proven they have produced amazing results. Where it has been applied, wherever it was applied, or it has been applied across different fields around the world. Yeah, so data analytics is having to do with crunching numbers and data generally. Yeah, mining data, manipulating data, torturing data, and creating amazing visualizations with data. But more importantly, predictive analytics. Yeah, because by the time you go into predictive analytics, that's when you start having things like machine learning, deep learning, computer vision, and natural language processing, and other things like that that are components of AI. Yeah, so they are still all part of data analytics. Yeah, so I think the most exciting part of the whole thing is when we come to machine learning, deep learning. Yeah, because these methods, these techniques have actually proven to be hyper effective, to be efficient, to be more productive. In fact, actually the main aim is to automate most workflows. Yeah, so generally you are trying to identify a certain facie, a certain lithology. This is what the normal petrophysicist would take a lot of time to do. Yeah, the petrophysical experts would take months to do. But with machine learning models, you can do that in just weeks or less. Yeah, so in fact, in less than a week, yeah, depending on how good your AI professional is, yeah, working with your experts or domain experts or domain professionals. Yeah, so that's basically an example. And by tomorrow, I'm going to be showing us more practical applications of data analytics in machine learning. If you are smart enough, you can come up with solutions to almost anything. So things like well log normalization, things like you can actually construct a completely missing curve from the ones that are available using machine learning. For example, you don't have, for some reasons, maybe due to tool failure or something like that, you had some areas where you have missing values in your well log curves or your well log tracks or signatures. And then you actually want to replace them. Or you don't even have the log at all completely. Maybe due to data management issues, or it was not even done, maybe because it was too expensive. You can amazingly construct a well log that would probably be close to 100% accurate or close to 95, 90% accurate as compared to when you actually put down a tool there and record and measure this thing, provided you have data sets from other parts of that field. Yeah. So you see how valuable it is. It could even replace cause the need to even do expensive current processes and in laboratories and all that. There are many, in fact, it's not just it could, it has, I mean, many organizations, many companies have been doing that. And you can see a lot of papers published on that, where they discovered there was no need to actually even call because they could use machine learning to get out these values, this porosity and permeability values, and that with such level of confidence. So there's no need going around calling around the field. If you just have a few core samples from a few parts of the field, what's the need of doing the coring all around? So they just use that and they're able to produce very close to perfect results. So it's vital you as a modern petroleum engineer, you as a modern geoscientist, you as a modern oil and gas professional, you are familiar with this, because even if you are not working in the core technical aspects, today I was discussing something about predictive maintenance. Yeah, so in my team. Yeah, so predictive maintenance having to do with surface facilities and using AI to predict when this facility is likely to break down. That would enable you to bring up proactive measures to avoid unnecessary downtime. Yeah, so those are some of the, I mean, you as a professional, it doesn't matter where you are, it's not just going to be really nice to have, it's becoming vital and important because as AI and data analytics is permeating everywhere, I'm telling you that they are the ones, domain professionals who are actually familiar with this technology are the ones that will control the industry in the very near future. So in this training, we are going to focus on petrophysics. Subsurface is a lot, yeah, but we are going to focus on petrophysics. And Praise the Corporal will take us through some very basic aspects of using Python programming to explore data. Because before you start building your machine learning models, the first thing you will do is to explore the data. So he will take us through some very basic things, and I'm sure it's going to be exciting. Just pay attention and be fully engaged. Ask him questions where you don't understand. Yeah, but by tomorrow we are going to build a machine learning model. Based on continuing from where Praise the Corporal stopped. So that's the presentation for today. Over to you, Mr. Ogolo.
Okay, yeah, thank you, Engineer Destiny, for a wonderful introduction to subsurface data analytics. I know the program is so power-packed, and what I always like your training is that it's not just only talk, but the hands-on session is usually very rich. So thank you so much, Destiny, also for honoring our invitation and for some of other stuff that we've also done together. So at this junction, I would want to invite Mr. Praise Ekeo Power, and just a brief about him, because I know many of us would want to know who is this guy that we have also been talking about. So Mr. Praise is a data scientist with a petroleum engineering background. He applies his knowledge and talents in areas such as finance, energy, healthcare, and IT to create impactful solutions. He has a long list of notable innovations, and solutions that have been published and now being peer-reviewed. Praise Ekeopara is currently employed as a machine learning engineer at TechPet Global Limited, where he collaborates with highly skilled teams to develop sound digitalized solutions for the petroleum and gas industry, as well as other industries. He coaches a variety of passionate students around Nigeria in his spare time, providing them with the necessary learning materials and advice. He also teaches part-time classes in data science, Python programming, BI tools, and other related topics. So you can see that we are well prepared for this training. So at this junction, permit me to invite Engineer Praise Ekeopara to continue with the second section of today's training. Thank you. Mr. Praise, over to you. Thanks.
Hello, good evening.
Yeah, good evening.
Please confirm if you can hear me clearly.
Yes, I can. We can hear you clearly.
Okay, so thank you very much for that wonderful introduction. And I want to use this opportunity to thank every one of our attendees for making our time to be here. And in the next few minutes to hour and half, we'll be walking through some important stuff together. So I would urge each and every one of us to pay attention. Let's enjoy it. Even when we'll be talking some advanced concepts, let's just enjoy it and flow through. So I'll be sharing my screen with you now. Okay. Okay, so please confirm if you can see my screen.
Yes,
see your screen, sir.
Okay, beautiful. So I'll be walking us through, as Destiny said, I'll be walking us through well-log exploratory data analysis using Python. So our outline will be outline of our discussion will be seen in two different sections. The section A will be making some basic well-log visualizations, which will involve loading our well data for section A, then setting up the log plots, then customizing the log plots so that we can get something that is good and something that is close to what we have been seeing conventionally. So since I have two sections, I'll be making use of two different data sets. So I'll be showing it to us shortly. Then in section B, I'll be walking us through well-log data exploration, which will involve loading the data for section B. Then we check data completeness, identifying gaps in the data. Then that will equally help us to see how data can be purified or can be visualized or prepared, then used for subsequent things. So this stage of data completeness will be a stage whereby we can identify one or two problems, especially missing issues, because that's the primary issue that we encounter whenever we are working with real life data. So after learning, we now plot some basic density neutron distribution by lithology. So we plot a density neutron log with respect to the lithology. Then we equally see how we can visualize density neutron distribution by lithology based on the well, because whenever we are working with our upstream data set, we're always interested in knowing the number of wells we have, because each well, most times they can behave similarly or differently. So we make sure that we visualize to ascertain what is inherent in one well with respect to the other, and that will help in our decision making and to equally guide us in how we can handle respective issues that are observed or possibly being observed in those different wells. Then in conclusion and next steps will be where we give some advice on how we can make further data modifications. Then for the sake of our time and so that I will make it to be interesting, there are some codes that I will be typing. the easier ones or the fewer ones, I will be typing them. Then the ones that will be too long or too lengthy, of which if I'm typing it, it might take some time, and at some point you might even be lost because I might just be speaking to myself and be typing the code. So to avoid that, I have already written down some of those codes. Then like all these spaces are where we are going to impute our codes. Then these are the long ones of which we are going to like discuss it together. Then this one also, and that's all. So another thing I would like to say is that, you know, before learning, we make assumptions, or before teaching, we make assumptions that people we are teaching, they have knowledge of programming, they have knowledge of this. So for now, I may not really guarantee that everybody here has Python programming skills already, so that we will just be speaking in the computer language and be going. So what will happen is that it's advisable you should be more interested in the concept, what we are using the code to achieve, more than understanding how the code is working, because even while explaining the code, I might be mentioning some terms that maybe you haven't had before, or might look somehow ambiguous to you. So just let's flow and get along with the flow. So for my data sets over here, I have two data sets. One is the well-logged data. It will serve for our section B. Then the other one will be our log, well-log explore data, and they're already in their CSV format. So they will help, that one now will help us in our section B. So let me stop sharing a little bit so that I can. So sorry I stopped sharing, but I will start up again. So okay, so we are back. Okay, so let's start. The first thing we want to do is that we want to start with the section A, which is well-log visualization. So we know our well-log that we usually visualize it, at times we have it as a single log, at times we have it as a combo log containing neutron, gamma ray, depth, and the rest. And we see how those signatures or those log tracks are observed while throughout with respect to depth. So we'll be making a kind of visualization like that. But before we do that, we need to import our necessary libraries. And libraries are just Python built-in frameworks that helps us in achieving what we want to achieve. For example, if we want to make visualization, there's a Python library that is responsible for that. So before we make use of them, we need to invite them, like import them. So I've been importing, first one will be the numpy as np. Then this as will just be the short form. Instead of calling this big or long name, I will just be using this alias, or also known as. Then I will import matplotlib lib.py plot as plt. Then I will equally import cborn. So these two, matplotlib and this cborn I'm typing now, will help us in visualization as CNS. Then I will equally import I will import pandas as PD. So pandas will handle our data frame, our data tabular display and everything. Then I equally import the missing no as MSNO. So this missing no is actually a library, a useful library that we use majorly for identifying and analyzing missing data sets, and identifying missing data sets, or checking data completeness for our well log data. So you can equally use it for other data outside the industry. So these are the basic libraries. Then if there is need for downloading or importing others, then we can. Then if you run this code and you find out that this one is not existing, it means that you need to download it. And if you want to download it, there are two ways. You can go to your terminal and download it using pip install. Then you mention the name like this on your terminal and connect your system or what you're using to download. Is going to download or install. Then if you want to run it on Anaconda, you can just do it this way and run. So, but I already have it, so there won't be need for installing it again. So the next thing now will be to load our data. And to load our data, I will need to define a data variable name known as well. Let's just call it well. You can call it whatever thing you need. And I will now be using the pandas data frame to read the data. So I will read underscore CSV. So the data is in extension CSV extension. Normally our well logs are usually in LASIO format. So this data, for the sake of the class, I've already converted it to a CSV file so as to make things easy. So based on the location of our data sets, I will now get well log data.csv. And if I run it now, sorry, I need to run this first one. Then I will now run this one. So I have my data, the well. So I need to get the 5 rows. And if I want to get it, we use our well dot the head to get this. And immediately we have our data. At least this displays only the first 5 rows, like 1, 2, 3, 4, 5. And in Python, it usually starts from 0. So 0 is our 1 is our 0 in Python, or something like that. So if I want to get the tail, like the last 5 too, I can use the tail and navigate and get the last values. So that's just that. Then maybe if I want to get more than 5, I can just use and specify maybe 10 and run it, and I will be having 10. So anyhow you want to do it, you just manipulate and have an overall view of it. So in our table now, we have the depth, we have the GR, which is the gamma ray, then we have the DT, which is the sonic log, then we have this, which is the density log, then we have this, which is the corrected density, then we have this, which is the neutron log, neutron porosity log. Then these are the various data set. Then if you check, you are seeing minus 999, minus 999. At some point, you'll be wondering whether our data usually has this. So how our data is collected in such a way that anywhere, most times, anywhere where our sensor doesn't capture information, at default, it replaces that place to be minus 999.0. There are some ones that you see 0.25. So to replace it, we now replace it with actual missing value. So to replace it, we do this well dot replace. Then we now mention that number we want to replace, minus 99.00. Then we now define what we want. What we want to use in replacing those values. And what we want to use is none, and we are getting it from the NumPy library. So we now use in place and change our in place to true. This will help us in correcting these values to the original data, which is this well. Then I will now run it. Then as we go on, I pray we encounter some errors so that we can see how to correct them and the rest. So next thing will now be to obtain the data dimension. It's usually a good practice to know your data dimension, so as to know whether you are working with a big data or not. So this shape, what it does is that it returns two values. The first one is the number of the rows, while this one is the number of columns. So the first one, which is the number of rows, tells us that we have a total number of 1,921 rows. Then this one is 16 columns. And if you check it, 1, 2, 3, 4, 5, 6. So next thing we do is that we want to get the columns, and these the columns. Then we have it to be depth, GR, DT, and the rest. Then another thing we want to we consider getting will be the data summary. And what do I mean by that summary? We can call it the summary statistics, whereby we want to get the mean, mode, the mean, the count, and the rest of our data. To do that in Python, you just use .describe. So this thing is actually basic in data analysis in Python. So we use the describe function to let us know the summary of our data. So here we have the count, which is, it counts the total number of data points for our rows. Remember, our total number of rows is 1,921. So for a complete a column, these are columns or features, or parameters. So for a complete parameter, it's assumed that they should equally have a total count of 1,921 across. But if you check here for the sonic log, you're having 1,980, which shows that there is possibly a missing value. And if you can remember, is that one still okay? Is that data that was containing -9999 that we now change to missing? Then this one is the mean. It calculates the mean across all the columns. Then this one is the standard deviation, the mean, the minimum value. We use it, and in our subsequent plots, we'll be referring back to this. Then we have the percentile, which is the 25th, the 50th, the 75th, and the maximum. So this helps us to know the nature of our data, to know which one is higher than the other, and to know the ones that are in zero or in decimal format and the rest. So we now begin our plots, and this our plots will be the basic plots, whereby we quickly make a subplot using a subplot 2-grid from Matplotlib. So I'll be making use of subplot 2-grid. You can equally make use of a different one, maybe subplot, or from even Seaborn or Plotly. So, but for the class, I'll be making use of this. And to do this, we need to first of all define and initialize our subplots with the size. And to do that, I just call in a name, let's say a variable name, call it fig for figure. Then I will do plt.subplots. Then inside it, I will be having figure size. So what I want to use this thing now for is to define the size of my plot. This should be fixed size. Fixed size. Then I'll now call it 10 by 10. And what do I mean by this 10 by 10 is actually the width and the height. So with this now, my total figure size will be 10 by 10. So I will now define the axis to be plt.subplot 2-grid. Then I will have 2 arguments here, like this. Then this first one will just tell us, let's just call it the location. Let's just call it the location or the number of plots that I will be having. So I have 1 by 3, which means I want a total number of 1 row plot and 3 columns. So I will be having, this thing means that I will be having 3 vertical plots. You know how our well logs usually are. Then this one will state the location. Then after this, the next thing I will do now is to define the row span to be 1. This thing limits my plots to be only 1 instead of having any conflicting plots. Then I have this one row span to be 1. Then the next one is to have column span to be 1 as well. Then since for now I want to be plotting 3 plots, so I will have this in 3 places. So I will just do copy and paste because it's just the same thing. Then I will edit this to axis 2. Then this one will serve as my axis 3. So I will edit the location. This one will be in, so this one is for row and this one is column. So I will change this to be 0. This one will be 0. Then this one will be 1. Then this one will be 2. So with that, we are now in order. So for the gamma ray track, that's if we want to plot our gamma ray, I will call it X1 because I'm assuming my gamma ray is the axis 1. I will now call it dot plot. Then I will now enter the gamma ray, and this thing I'm entering now is the name of this column. Then I will now call the depth because I want to plot it against depth. So this first one is usually the x-axis, while this one is the y-axis. So I will now continue and state the data. And the data I'm using is well, because that's what I named it over here to be. Then I will now be having the color. The color, I want to call the color to be green because it's usually green from the normal plots we have. Then another thing I would like to do is that I would like to set the the title. So I will use the axis 1.set title, and I will call it gamma. Then another thing I would like to do is that I would like to set both the x limit and the y limit dot x set x limit. So it's just like the limit of what the data will be like. So if you check the gamma ray log, we have the minimum to be 19.6. So I can call my own, I can just call it 19. And the maximum we have here is 137.46. So I can just call it 140. So I will call it 19 by 140. Then another thing I will now have is x1 dot set y lim. Y lim will be my depth. So we come over here and check our depth. So depending, your own data might be different from what I'm working with, because this is like a section of a complete data set for the purpose of the class. So the minimum is 4,609. So I can call mine to start by 4,600. Then the maximum will be 4,900. Okay, or I just call it 4,810. But mind you, this time around, I'm going to reverse the depth so that it will be from kind of shallow down to the depth, because while we are drilling, we are going from the shallow point down to the deep or the deeper section of the subsurface. So I want to stay reverse such a thing. So I will now be having my first to be 4,110 by 4,600. So another thing I would like to do now is the grid. This one will help to generate the grid, all those vertical and this grid will help us in the vertical axis behind the plot. So with this now, I'm done with the one of the gamma ray. I will now copy the code because it's still the same format. I will just do little editing. So if I want to edit now, the one I want to plot next is the density, and look at the density plots here. So arrow HOB. So I'll just change this to arrow HOB. Then I will change this one now to density. Then I will change the color. Possibly I can decide to call it red. Then another thing I need to change is the limit. And the limit for this one varies with the other one. So is the limit should be, let me just use 194 or 19 to 2.8. So 19 to, let's say, 2.8. Then same thing with the depth and the grid. So I will edit this thing now to be x2, axis 2, sorry, axis 2 or true. Then everything has been edited. Then I will still copy the same stuff and paste it because I want to plot at least 3 plots over here. Then the next one I want to plot is the sonic log, which is this DT, and the minimum and the maximum. This one is 54, this one is 89, so I can call it 50 and 90. So to achieve that as well, I will now edit this one to be DT, then call this one sonic. Then I will now have this one to be 90, then 50. So I'm like reversing this one also. So with this now, I'm done with the plots. The next thing now is to go through my code. Okay, I have this to be 3, then 3, then 3. It needs to be 3. Need to be 3. So I need to change this color. And let me just give this one maybe a purple. So you can still choose yellow or white or anyone you want, but make sure the color will showcase what you want to do. Then I have everything in place if possible. So let's run it to check. Okay, good. There's no error. So we have our first simple visualization whereby we can see the gamma track or signature, then we see the density, then we see the sonic. So at this point in time, this is now where the interpretation comes into play, but I will leave that one for you based on your knowledge, but this is just how it's done. If you observe that the gamma ray was so increased, which we can suspect to be a shell formation. At some point it declined, which is sandstone or limestone formation. Then at some point it increased again. So that's a signature, that pattern. So to respond to that, our density was equally increasing to this point, then suddenly started decreasing at this point. So, you know, when we are interpreting this stuff, we don't interpret with one single log. We might combine one or two to make some conclusions. So this is the sonic log and the plot. So this plot may not actually look interesting, and we may not actually extract much meaning from it because it's just the basic. So we size and more customized log plot, of which I won't be typing the code because if you observe the time it took us in getting this one. So we can further customize the plot to look more like a familiar log plot with the curve names and scales at the top and 2 curves, density and neutron in the one track. So what we want to do now, you know that in our conventional plots or traditional plots, we usually have our neutron density plots together, like converging. They can either overlap or have a butterfly effect or something like that. So depending whether there is oil or gas. Okay, so to make that plot, I will be having a more interesting codes that we handle it, because if you want something beautiful, you need to go extra mile. So it will be looking quite different a little bit from our plot, our codes previously. So will be our result. So let me just explain it. At this point, we are having we are defining 2 parameters that will represent our plot. Then we define the figure size to be 15 by 15. So this time around, we are increasing it 15 by 15 because so as to avoid any overlap or shrinked plot. So as usual, we'll be making plot of this time around, it will now be 4. even though we have two that will be like twins, then we know our axis 1, axis 2, axis 3. Then the next one will be our axis 4. But this our axis 4 now will be axis 2. And you know, axis 2 in our previous slide is where we have the density plot. So this axis 4 now will eventually be, since we have defined the neutron plot, the density plot, then the next one will now be the neutron plot, and is possibly going to be our axis 4. And we now use this method known as dot twin or dot twinning function, so as to make both of them to like agree, or we just marry them both. So we define twin tracks for others and set their visibility to false. So what you did for people in team A is the same thing you do for people in team B, for them to work together. So that I'm just like trying to give us a scenario. So if we were able to give axis 4 a twin, so for this plot to be okay using this subplot 2 grid, we need to equally give others their own twins, and now set their visibility to be false. Okay, false to be false. So that's what we'll be doing. So I will change this to be false. This is supposed to be false. False. Then I will set this one as well to be false. So so I will now change it to be false, so that they won't show. The only one that we show will be this axis 4. So everything is now balanced. The next thing I will now move over will be to the gamma ray track. And in this gamma ray track, as usual, we use this one to define it and set the color. Then we use set X label to define the name, as well as other parameters that will be accompanied to it, such as the axis label dot set color. Because we want a more advanced plot, we want to ensure that even our labels, that's what I mean by labels, our titles are equally colored. So those things are things we want to achieve. So that's why we have this dot X axis. Then we have this one to be dot X limit, trying to define the limit. And that's what we have in our previous codes. Then axis 1 dot set Y label to be depth. So we want our Y label to be depth. That's the vertical axis to be depth, and the name we are giving it is depth in meters. Depending on your data, it can be in feet. Then we have our axis dot tick parameters, axis to be X color green. So we are still trying to like color a kind of the X parameter. When we visualize it, I will be coming back to all these things. Then the top, then the spine top dot set H color. So I want it to be at the top. Now the plots and everything, their labels will be on top. Then I have the same thing, set the color to be green. Then we set the X ticks to be this. So this X ticks, just see it like when we are trying to label something or calibrate something to be 0, 50, 100, 150, 200. So when you are now seeing the on top of our plot, you are now seeing a kind of calibration, and calibration is very key, is very vital, because it helps you to easily glance and understand what how your curve or signatures or tracks are running. Either they are running from a decreasing side to an increasing side, or from an increasing side to a decreasing side. So that's just the reason for this X ticks. Then same thing for the density, we make the same thing, set its own X ticks. Then the one for the sonic, we set it also, but this one we didn't actually give it an X ticks because possibly we just left it, even though we know that. And the truth is that this axis too, even if we don't include it, it's going to have, it might possibly suggest its own axis labeling, but we try to put it there so as to be the ones to define it, so that it won't come out at default. So we don't really care about this sonic. So anyone it comes out with, any of the X ticks it comes out with, we equally make use of that. Then for the neutron track, this is where we now need to pay closer attention because that's the new guy that we want to add. So we still defining like others, set the color, set the X limit, set the Y limit, set the tick parameters, then make sure we have the spine stop, set position, the spine stop, set visible to be true. So it's the only one we made its own visibility to be true. So then we set another one, the edge color to be blue, then we assign a kind of X ticks to it. Then this is the looping section. And in this looping section, what we do is that there are more characteristics or attributes we would like to add to each and every one of these tracks. But since it will just be like repetition, even some of these ones self that are repeated, I can equally put them in loop, just that the ones we put in loop are the ones that are generic, such that it can work for track A, work for track B, work for track D. So we just use it to put it everything together. So some of those things we now loop AX in axis X1, axis X2, axis X3. We now make sure that their limit is this, then their grid, which will be major, then their color will be light gray, then their line style will be kind of thin, straight, thin line, even though they are not going to be all that straight. Then we set the axis to be top, so all of them will be top, then set position to be axis, comma 1.02. This 1.02 is just like the spacing of the axis. For example, if you increase it to maybe 0.8 or so, you see it will be the label will be far away from the other one. Same thing with this thing we are seeing here, 1.08. Then this plt.tight layout helps us to like compress the data so that they compress the plot of the visualization so that the layout is going to be in a compressed format and won't be all that, how will I put it, be all that random or unorderly. So with this now, we can now still go back to our code, check, then run it and see what the result will be like. Wow. So we have the results to be something like this. Okay, so we have neutron, we have density. The space here is much. Let me edit it a little. Let me change this to, let me just change it to before and see how it will look like. Or it's merging together. So let me change it with 3, let's say 5, and see how it look like. Or it's still overlapping small. So let me check 6. Okay, I think 6 is better now. We are seeing density, we are seeing neutron. So our interpretation still continues, or you can still interpret. So based on this now, we are having the neutron, the density, and both of them overlapping. Then in the region where we have sandstone, you now check the neutron density plot or is plot to know. I won't really be interpreting it, because at times when they like do like a marriage or so, we suspect oil to be there, we suspect. Then if there is an overlap, then we suspect gas. So based on that assumption and more advanced assumptions, you can still now know whether at some depth you'll be expecting an oil or so. Then we will still decide with only these 2 plots. You can have many plots as possible so that you can know if that place is occupied by water and the rest. And again, another important one is the resistivity plots that helps us to differentiate whether the formation is majorly composed of water, gas, or oil as well. So at least we have seen how we can make a customized plot. The label green, then this one is blue, the label is blue, then the calibration. This was that X6 I was talking about, the density, the sonic log, and the rest. So with this, we have seen how we can easily make some plots well log plots. So we'll be moving to section B now, and this section B will now be where we'll be talking about well log data exploration. So as usual, I will be getting my data. So let me quickly do that because we'll be having a whole lot of visualizations over here, as well as the explanations. So we have pd.read underscore CSV. This file is equal in CSV. So depending, your data can be in a different extension data sets. And this one is called well log explore data.csv. Then let me run it and check. So we have the data. So instead of using well name is for the previous first data set, but this second one is now the well log. We named it well log, so we'll be calling well log. As usual, let's get the head. Then for this one, we can see that we have a total of 29 columns, then 5 rows. Then we have well, the name, the different titles. We have the well, the depth, ND, that's the measured depth. These are the well types. Then we have X log, Y log, Z log, group, the information types, caliper log, and the rest. So let's get the dimension so that we know, be conscious of our data, then use the shape. Okay, wow. We are having a total of 133,198 rows of the data. Then we have a total number of 29. They have a total number of 29 columns. So let's display the columns. Well, log dots. So to display the columns, we use dots columns. Then we have them to be, so we can see the well log and the good number of them. So as usual, let's get the summary statistics using the describe. And this describe will give us like a summary statistics, and we can see some of them here. Then another thing we can do is that we need to get the well log. We need to know the number of wells we have, and it's usually a good practice and advisable for any upstream data you are working with, or either production, maybe reservoir data you are working with, or well log data you are working with. Make sure you try to ascertain the number of wells you have, especially for our well logs. Know whether you have 30 wells, 40 or 50, so that you know how to deal with it. So to ascertain the number of well logs we have, I will now use this method. Hereby I will call it well. I will call it well. Let me check this spelling. Okay, capital letters. Then I will now use this dot unique. So this actually tells us the uniqueness. Unique. Then I will run some seeing different well types. So to know the exact number, like I may not really count it. If I count it, I can get it. But what if the well types are too many that I can't count one by one? So to do that, I will simply copy this code, paste it here, and before the unique, I will just put n, which will calculates the number for me, and I have the total number of 12 wells. So with that, our subsequent plots will be revolving around 12, 12, 12, because our number of well types is just 12. So now it's time to check for data completeness. So we want to check how complete is our data, what are the different techniques we can use. So I'm making use of that library I told us about, that library known as the missing no library. It helps us to visualize, to understand how complete our data is. If there are missing values in our data, we now handle them. And why are we stressing about missing data? When working with real life data, it's not usually clean. It comes with, at times, they can come with serious dirty stuff. So what we do is that we handle them. And the most important of them all is the missing data. And missing data is not usually the fault of maybe any person. It can be a collective fault or so. So the blame should be shared. So it can be as a result of possibly our censoring tools didn't work well. So they just malfunctioned and they didn't capture some certain depth. Then because some of all those, our sensing tools, while they are going under high pressure and high temperature, some of them, those temperature, encounter temperature might be above what they can condone. So in such areas, they may not actually pick the data, and that's how that will result in a missing data. Another thing can be maybe human error, possibly when the data was being handled, or so one or two data points were deleted. Another one can be maybe management error. The pipeline wasn't well monitored, and there might be a recurring issue or problem that usually deletes or doesn't really capture all the data. So many things can cause that. So to visualize that, we now call that library, we called MSNO as the alias. Then we now do .bar. It's just simple codes that will be producing wonderful things for us. So we call the name. So what you just do is that you just call .bar, then enter the log name, and you plot it, and we generate a bar plot for us. And this bar plot can be interpreted this way. Here we have all the different columns or column names, where we have our well, the measure depth down to the end here. So the height of all these bar plots, what they do is that they represent how complete our data is. So if we have a complete bar height, or so, you now know, you can say that this well is kind of the data points are complete. Then as you can see, you are observing some that are shorter. The one that is having the highest number of missing values is the RMIC. It's very poor. So you can use it to like see each column that is having missing value. So before I make the other plots, another good way you can still do this is that maybe you can call the well log and use is null .sum. Then this one now will help you to calculate the total number of missing points across all the columns. So for the well, we are seeing, okay, let me zoom in a little bit. So for the well, we have it to be 0. That's why it's complete. Then the depth, measured depth, we have it to equally be 0. That's why it's equally complete. Then the X log, the Y log, and the rest, we have them to be shortened. So these are a few ways we can use this Python to identify missing values. So you can see it. Then if you can remember, our total number of data points is, I think, 130-something thousand and some figure. So if you check the one that is least, which is RMIC, if you check it here, we are having it to be 130. So almost like 98 to 97% of the data in that stuff, in that column, are just all missing. So that's just it. So we need to still identify it and know how to handle it. So most cases, there are different ways of handling it. You can decide to like remove it entirely, remove the column, or you can decide to like impute, possibly using measures of central tendency such as mean, mode, median, or you can equally develop a machine learning model that will predict, just as like Destiny said, you can use it to predict, but this time around you are predicting for the missing values. So there are many ways to do it. And again, in our oil and gas data set, we are usually careful whenever we are working with the data. You don't just look at a data and you start deleting, or you don't just see a data and you start maybe doing one or two data wrangling or data manipulation techniques, because each data column or data point have and must definitely have it must have a kind of impact in real life. So anything you are doing, you need to be careful, check everything before taking decision. So this is just like a simple way of getting the sum. Another way we can still visualize this missing data point is by possibly making use of the MSNO dots matrix. So we want to have a matrix, then we call the data name log. So with this, we have it to be this way. So this is actually the same thing. The height of all this stuff tells us, equally informs us. The black charts equally tells us how complete our data is. Then the white spots are where we are finding missing value. Then at this point, this right-hand side, we have what we call the spark line. What the spark line does is that it sends us along this vertical axis. It sends us where across all the features, feature 1, 2, 3, down to the end, where we have complete data. If we have complete data, it increases, it goes to the highest peak, then it keeps on increasing. So if you check here now, we have missing value here, we have missing value here across. So that's why it's at this height. Then when it went here, it increased. And if you possibly check across here, there might be more present value across others than this lower one. Then you have it across all. So it equally tells us about the missing data points. So another one we do now is that we want to use matplotlib, because we need to apply various ways of identifying missing points. So I've written this code already. I'll just type a simple code which will help us to continue the plot. So if you see in this code now, I have grouped. I haven't defined it, and that's what I will define. So what I want to do here now, let me explain first before I start typing. So what I want to do here is that I want to create a new column, because for the kind of plot I want to make below here, I want to develop a new data frame or new data, whereby all these petrophysical and geophysical parameters will serve as my columns. Then their various data points will be like a measure of their number of actual data points present in it. So that's what I want to achieve in this code. So some labels useful to geoscientists and petrophysicists include well depth, measure depth, caliper, gamma ray, bit size, density, neutron porosity log, photoelectric absorption log. Then this one is the deep resistivity, the medium resistivity. Then this one should be compressional sonic log. Then this one is the shear sonic log. You can equally look out for it to confirm. So to do this now, I will define. Okay, let me just go straight to the coding proper. Then I will now pick all of this, paste it here. So I've gotten the data. So I will now need to look for num column in enumerate. So inside, so I will now be having data none dot columns, then and I have it to be 2. Why I'm calling 2 is that I want to exclude this well and depth. So I will now have data none column. Then I will now have data none. It should now be the column dot. I want to check if they are not null. If they are not null, what this thing now will return is true or false. This one now. Then if it's true, it's going to continue with the value. Then if it's false, it will return a number, and that number will be num plus 1. This num here, based on this enumerate function, this num will be for the index. Then I want to add the index 1 because index starts from 0. So I want to add it 1 so that if we are having index of 0, it will be, the actual value will be number 1. Then if it's index of 1, which is 2 in the renumbering system, it will now be 1 plus 1, and it will now become 2. So that's just something I want to do. Then if I run this code, I will equally be getting some zeros, of which I need to take care of. I will replace the 0. I think I have used this replace function. I replace anywhere I see 0, I replace it with num. Then in place, my in place will be equal to true. Then to test it, I will need to print column, which will be the feature name, and the num will be, which will be the index name. Then I will now define a name I will call grouped, and this grouped is what is here, or what we run here when I run it. Then this grouped will be, now what I want to do now is that at this stage, I want to group all the data, or all the data frame with respect to the where types. So we have a total of 12 wheres. So I'll be having 12 rows based on the type. So if I want to group it, this group is just like takes the average. So I will now have data none dot group by. Then I will now have it to be well. Then I will now run it, invalid grouped. So, okay, I didn't cover this, so that's why I'm having a syntax error. So I will now run it. And if I run it now, I'm having a caliper to be 0, GR to be 1, PS to be 2, arrow HOB to be 3, and the rest. So they measured the presence of missing of ray values in my data. So this, you can just call these numbers like an increasing number or so, but we will appreciate it when we run this code here. So in this code now, what we want to do is that we want to generate a very encompassing plot such that the respective where logs or where types will be represented fully. And for each where type, we are going to have a measure of this caliper, gamma ray, bit size, and other parameters being represented with respect to their number of present data. So this is why even in the whole machine learning process or data analytics process, exploratory data analysis takes the highest time, because you need to be sure, because computers are garbage in, garbage out. So you wouldn't like to garbage in something that is wrong, because possibly in the nearest future, even when it's deployed in real life, it will be garbaging out rubbish as well. So we need to make sure. That's why we can plot like up to 3 or 4 plots. I've observed that most cases we have observed that what one plot may not show because of the nature of that particular data set, another plot can either show the same thing. So that's why we need to still make some plots. So we have the label to be this, which are those parameters. Then here we now define the axis subplots, and inside here we'll be having 4 by 3. And what do we mean by 4 by 3? We are considering 4 rows and 3. We are considering 4 rows and 3 columns possibly, and not even that. We are considering 4 and 3 because our total number of wells, our well size is 12. So 4 times 3 will give us 12. So that's why we have that 4 by 3. So if our well type is possibly maybe 6, we might be considering 2 or 3 by 2 or something like that. So all those things are things we equally consider. Then we have our 4. Here we are going to loop. And this looping we want to do here is just like a code that we accomplish these tasks, but we can equally have more complicated codes or equally more simple codes. So what we want to do here now is that we want to create a kind of a data frame or a kind of plot. And this and when we create this data plots for the respective wells, we set their x limit and their y limit to be this. Then we are assuming the depth is 5,000. It can be 4,000 or so, depending. Then we use this ax dot fill between x. What we want to do is that we want to fill that area. This dot fill between, what it does for us is that it fills the area for us. And for the first one, we are filling with respect to depth and then we are filling with respect to depth, and we assign it to be 0. And why is it 0? Because we have a total number. Let's count it: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the one we want to plot will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's why we have 0 to 9, which is actually 10. So we want to fill for dot caliper dot gamma dot bridge size and the rest. Then we set their face color to be gray. We set their face color to be gray. Then the other one, which is for the gamma ray log, still the same format code. Then light gray, medium, sea green, light blue. We can keep on varying the color with testo and the tan color and the rest. So we have many colors. You can Google it and get as much as you like. You want, if you don't like the one we have here. Then this code handles our grid, then our X sticks as well. The minor will be false because we don't want it to show per se, because we just want to use it to show that what we have are 10 parameter types. Then the minor would be false. Then the x6 would be where we have 0.5, 1.2. So this one just sit like this one handles the minor one, like the minor is like false. Why this one now is like we want to make it true because we need it to be in such a way that even though the numbers won't appear, but we want to stratify so that it will follow a small shape and defined shape across all the plots. So I think I need to plot the stuff first before I say too many things about a plot that I haven't plotted before. Okay, so we now set up the ticks and the labels, and this where we set up the ticks and the labels, vertical, minor through vertical alignment to be bottom, the x-axis, the minor, the pad, and the rest. Then this one will serve as our title, and we want the font size of our title to be 16. And this title will be the names of the well. The names of the well. That's why we have name here. And if you check, we have a name over here. So we want our individual well names to be this name. Then the font size will be 16. Then the font weight will be bold. So we want it to be like a black bold stuff. So this where we define the color to be black. Then we now make a PLT plots, adjust it to headspace of 0.15. Then if you want to still know all these things, you can read about the documentation. Then if possible, if you won't read that, you adjust it a little bit and observe the changes. Then as usual, we have our plt.tight layout to be activated. Then if I run this now, I will now be having these plots. So look at the plots I have here. And if you check, we are having various well types. Some of them are repeated, and well 15 by 9 to 13, well 15 by 9 to 15, and the rest. So this is just all the wells. So let's check the missing values. So if you check, you will see based on the color we assigned, the well types, like this well type now, which is 15, 9 to 15, if you check, is almost complete as of when you compare with others, like this 16 by 1 to 2 and 16, 10 to 2, 10, this one also. Then we have some of this one. And why this thing is good is that because we want to ensure the accuracy of our model, if our case is that we are building a model, what we usually do is that we try as much as we can to build the model with the truest data sample available as much as possible. So if we have a more complete data set than the others, it's usually advisable you make use of such wells that are complete to train your model. Then you can now test with any of these ones, or equally test with a complete one, or the one you will complete. Why? Because we want to acclimatize our models with the truest real life or close to real life data as much as possible, so that when the model must have been developed and deployed and it's encountering real life data, it will still perform well. So that's what we are doing. So if you check, you are seeing some that are missing, then you see some that are complete except others. So this is just it. And we are doing this across all the plots. So that's a pretty thing to take note of. Then I want us to move over to another, and this is like the last part. Because of our time, it's just like the last part, whereby we'll be walking through the various density neutron distribution plots and the rest. So what I want to we'll be making use of our lithology types. So in our data, let me print it out again. Have it to be well log dot columns. Sorry, it should be X. So in this our data, we have this one known as the first lithophase lithology. Is the one that is bearing all these codes, 30,000, 65,000, 30, and the rest. And they are representing different lithology types. So what we want to do is that we want to make some plots based on this sandstone, and we won't be making them using these numbers because we can't easily identify which number is representing which, but based on this legend, on this key identifier table we have here, you can identify that sandstone was coded with an ID number of 30,000. So what we now do is that we want to like merge it together, and to do it, lithology, we call a variable known as lithology numbers. Sorry, lithology numbers, and here we want to use a dictionary to assign them and see what we want to achieve using this dictionary. Dictionary is a data structure, in Python. So I'll just copy the whole of this, paste it here, then it's already aligned, or possibly I can do it this way to arrange it properly this way. It's It's usually like this, then I can do it this way to align all of them, even though that initial one will work, but let me just align it so that for convenience sake, you'll be seeing the data very well. So with this now, I have called all of them to be under lithology names, then I will run the code. Then what I want to do now is that I want to create a column in our original data set that will contain these numbers, but rather in the actual values. And if I want to do that, I will now define a column name and call it, maybe, let me just call it lit, which means lithology. Then I will now call the lithology we have. Then I will copy this guy here because it's the one that is having those numbers. So once I have called it, I will now use the dot map. What map does for us is that it identifies, okay, let me type this thing first, lithology and numbers. So what it does for us is that it tries to assign this sandstone and the rest based on a similar number code that this one is having. It exchanges it and takes the numbers here and replaces it with this one. And at the end of the day, we are achieving a column known as lit. So that's just the little I can give as explanation. Then at this point now, we want to make a plot. And for this, our plot, I will just copy and paste to do others. So I will be making use of Seaborn now to make this plot, which is Seaborn facet grid. Then I will now have a well log, which is the name. Then I will have a color. The color is like what I want to make the plot with respect to, and it's going to be with respect to lithology. Then I will call the color wrap to be 4. Then once I'm done with this, as we're checking my spelling, then I will do fig.map. Then in this map, I will now call CNS, which is the seaborn.scatter. So what I want to make is actually a scatter plot, and scatter plot. Then I will now enter the 2 arguments. And what I want to plot is the neutron density plot against the neutron. So the first one, which is the x-axis, NPHI. Then the next one will be arrow HOB, if I'm correct. Yes. Then I will now state the alpha. Define the alpha to be 0.95. This alpha tells us how thick our line plot will be like, or our plot's intensity will look like. So once we are done with this, we now do fig.set x limit to be equal to, let's say this one, I can just call the x limit because the one that will be in x will be the neutron porosity. I can just call it to be minus 0.15. Let it start from that range to 1. Then I'll still do the same thing for this one. So let me just copy this and paste. Then I will change this one to be y limit. Then change this one to be it will run 3 to 1. Then with this, I'm done with the plot. So let me run it to check if it will plot or if there will be any error. Okay, so we have our plots here. Very good. So we are seeing them to be white all over the white spaces. So I can choose to like edit it. Maybe I will use plt dot style dot use maybe I will use Seaborn. This is just for the background so that it will look better. And then if I run it, I will check it out and see what's going to be like. Okay, it's going to come out this way. So if you check, you'll be seeing the density against the neutron porosity log for the various formation types. So it's just like we are plotting neutron against density against neutron. So if you check across this plot, you will find that like the major or the one that is thicker or more intense than others happens to be, I think, more of the shell and the sandstone as well as the limestone, which might still be part of the sandstone. Then if you check it, it means that majority of our depth formation types are the shell, the sandstone, the limestone, and others. While the ones that are least are these halite, coal, chalk, and these anhydrite and dolomites and the rest. So this can guide us to know the different lithologies that are composed majorly in our, when we are considering the density neutron porosity plots. So, and we have achieved it using this. So I'll be copying the same code. So I don't need to copy the Seaborn or the style use because it's now in the environment, it's running behind or in the background. So what I will do now, I will make this plot there and I will drop it here. Then what I will now do is that I want to plot this density neutron distribution plot by lithology and the West. So I want to look at how all these plots can be with respect to both lithology and with respect to both the well. And I want to, I will equally be adding the legend as well. So, and that legend will help us, it will just serve as what will help in identifying the plots that we have or for better interpretation. So I'll just make little changes. For this one, I will have the color to be well this time around because I want to check it with respect to well. Then I will be having another one, which is the hue. The hue is just like where I want to concentrate the something on, like we will be having concentrating the scatter plots on. So it will just be with respect to lit. Then the color wrap will equally be 4. Then with this, I have second plot to be this scatter plot as well, neutron porosity log, density log. Then another thing I can do is that I can change the line width to be that alpha is running behind, so no need of adding it. Then the line width will be 1. Then okay, so we have the line width to be 1. Then another thing we need to have is the size as well. And the size should be 0.1 as well. 0.1, we can equally increase it, but I just want the size to be a little bit. Then we can have the marker, to be this to be plus. This marker is just shows us how our dotted lines will be like. Instead of being a dot, it will be a plus sign. So I will just edit okay, I will just add the legend dot add legend legend. I add it. So with this, I have added it. Then we can make the plot and check if we'll be having an error. Okay, everything should be in place. Let's wait for it while it runs. At times, these things can take long depending on what you are plotting. So let's zoom in a little bit and see what we have. So we have the different well types with respect to their lithology. So this legend here now is showing us the color. And based on this color now, we can now know for each wells the dominating lithology types present or what can be found for those different wells. So in well this, you can, in well 15.9.5, we have this set of colors. So if you check, possibly we have the green here, the pink, you can come over here and pick out you can see the one of the green here, which is the limestone, and the rest.
It seems he's having network issues. Let's just bear. He will be back shortly. So he's joining us shortly. Let's just exercise a little patience. He's coming on board. Thank you. So a special good evening to everyone. Sorry for the technical challenge that we had, because I think Mr. Praise is having network connection issues. But the good thing is that he was almost done with the parts that I was taking today. So on this junction, we'll bring today's session to an end, and the SP Abuja section would really like to thank everyone for joining us for this today's training program on subsurface data analysis. We thank the section chair that stayed throughout the program and other distinguished participants. I could see a representative from our own student chapters present here today. So we say a big thank you to everyone, students and professional members from other sections here in Nigeria. We say a big thank you for joining us for today's program. Like you saw that we posted a link for you to register your name, because after the training, we tend to give certificates to every participant. So I know so many of us have questions to ask. Due to the network challenge we have, would appear that you kindly note your questions down so that tomorrow, faithfully, we will be taking your questions. So today's session is done and dusted. I want to say a big thank you to the speakers, our distinguished speakers for today's event. The first is Engineer Destiny, is my very good friend. Thank you so much. And also thank you, Engineer Praise, my first time seeing you, and indeed, I want to say that you've done a big justice to this training today. So I want to say a big thank you to the speakers. And just to remind you, tomorrow is another one. So we'll have the second aspect of the training. As you saw today, this is just the tip of the iceberg. So tomorrow we'll still do more and more amazing stuff. So we appeal that you join us, because for us to be able to issue the certificates, it has to be based on your attendance. So we look forward to seeing you. Join us for tomorrow's session, which will be taking place by 11 a.m. tomorrow. So we appeal that you kindly put that down. So also to the link for the data sets as posted there. If you don't find it, you can easily DM me so that I will share it with you. And some other materials will also be posted to the Google Drive link so that you can access, because the goal of it is that we don't just want it to want it to be a thing of presentation, but rather it's more of hands-on, so that on your own, you'll be able to do it. And that is the main essence of this training. So a big thank you to our speakers once again, and a big thank you to every participant. So on this junction, I would want to bring today's program to a close. So look forward to tomorrow's session. I'm so excited. I can't wait for tomorrow to reach, because I know tomorrow will be another exciting session. Having someone like Destiny, having someone like Praise is an amazing opportunity. So guys, have a wonderful night, and see you tomorrow. Bye.